Hello, my name is Andrew Ferlitsch, and I'm a staff member at Google Cloud AI Developer Relations. Today, I'm going to talk about neural structured learning, which is sort of an advanced form of batch regularization. And its purpose is to help when you're training the model to even more generalize it once it's deployed, being able to recognize images and classify them or perform other tasks that may not necessarily be perfectly in the same distribution as your training data. Now, the first time people were really introduced to this was really just recently at the TensorFlow first ever Dev Summit on March 11th. And they gave three separate presentations on them. They all were about 20 minutes apiece, but they were very technical, a lot of statistics, very data science. And I kind of felt watching this that when it came to, say, the regular applied machine learning engineer, it would have gone over their head. But I kind of felt that the concepts they were talking about were really easy to explain. So that's what I'm going to do here today. I'm going to put neural structured learning into what I call machine learning engineer speed. And I'm going to do it with a single picture here. In this case, I say my picture here is worth 1,000 examples in a training set. So here we go. The theory behind neural structured learning is that if my model was perfectly generalized, then if I took an example, a sample, an image, and I took another image that was almost identical, that when both of them went through the model, when I come out the other end before the softmax, but simply when I come out the dense layer, the probability distribution should be identical. Okay, so that's the premise. Okay, so here's how they do it, or here's how I'm going to show to do it. You take your batch, you got your training data. Let's say it's cats and dogs. I'm going to do batches of 32. I draw 32 images out, 16 are cats, 16 are dogs. I'm going to make another batch. It's an exact copy of this original batch, but I'm going to do some random transformations to it. I might zoom in, I might shift it, I might rotate it, I might change the brightness. Both these batches are going to go through the model at the same time. So I'm actually giving a batch of 64. Think of this as the true batch. This is the batch we're going to use to train the model. This batch we're doing something different with. So we come through out of the model, right? And we get to the end of the model to what we call the bottleneck layer. Now, if you're not really familiar with the term what a bottleneck layer is particularly in a convolutional neural network, it's the last layer after your last convolution. So you have this set of feature maps. There's usually a large number of them, and they're very small. Okay. And what we're going to do is we're going to do a split. We want to split those feature maps up to the set that belongs to the true batch and the set that belongs to this mirror batch where we've done these random permutations. Both of them are going to go through the same trained dense layer, okay, where we're going without the softmax activation. So at this point, it's still a linear activation. And we're going to get that pre-softmax distribution, also known as the soft labels. If our model was perfectly generalized, in theory, the distribution here and the distribution here should be identical. And what we want to do is when it's not identical, the difference between them, we want to use it as a penalty to the loss function when we're calculating and updating the values of this weight for this batch. Here, we never update any weights for this batch. This is used strictly for a penalty. So if they were perfectly generalized, this L2 loss would be zero and there would be no penalty. But if we're not perfectly generalized, we're still trying to train this model to do representational learning. and learn only the essential features, what ends up happening because of this penalty starting kind of high is part of the optimizer minimizing. It's not only minimizing the loss between the true label and the predicted label, but also the penalty. So slowly and slowly and slowly, this process, this branch helps aid in training this model to generalize versus memorizing. And this is also very comparable to what some of you are used to called a pretext task in training. It's a pre-training operation in self-supervising. We're going to take some data set. The labels don't matter on it. It may be even unlabeled, but it's part of the data set or representative of what we're going to train. And we're going to do some transformation to it, such as breaking it into a jigsaw and changing the order of the things. And on the other side, we want to predict the transformation. Okay. And the desire of doing that is that we're trying to get the model to be numerically stable and to kind of sort of get the weights already in the direction of learning essential features, and then we do the real training. Then we start the full training. Well, what I really like about neural structured learning is essentially it's the same thing, except we built the pretext task right into the model, and that the training, the pretext training, and the data set training happen in parallel at the same time. So that's neural structured learning in one picture. Thank you.